Hey guys, my name is Z and you're watching MakesItEasy. And welcome to IGCSE Physics series. And today we have topic 2, which is solids, liquids and gases. So here are the lessons for this topic. They are density, intro to pressure, pressure in fluids, height and pressure, and for separate signs or triple signs, energy and change of state, temperature time graphs, specific heat capacity, investigating specific heat capacity, Kelvin and absolute zero, speed and temperature, pressure-temperature law, and Boyle's law. So moving on to the first lesson, we have density. And here's Archimedes' principle, which is when the body or an object is partially or completely immersed in a fluid, it experiences an apparent loss in weight that is equal to the weight of the fluid displaced by the immersed part of the bodies. So here's a diagram of the Archimedes' principle. Let's say this thing is here. It displaces, and here's the amount that it displaces, which is 3 pounds of water. So here's the equation for density. The density of a substance is the mass per unit volume, and for a symbol for density is rho, a Latin word, m divided by v, which is mass and volume, mass in kg and volume in m cubed, and density, which is kg divided by m cubed, which is kg m to the power of -3. And the more mass in a given volume, the greater the density. And here are some example questions for density. Calculate the mass of copper in a wire of volume 3 times 10 to the power of -5 meter cube. And the density of copper is 8.96 gram per centimeter cube. So first you have to convert this g/cm cube to the same as m cube. So just convert it like this, and here's a conversion. And then you just get m with this equation right here. And number 2, calculate the volume of a golden ring of mass 0.011 kg, and the density of gold is 19.32 grams per cm cube. So you can just convert this back to grams, because this is grams and it's much easier to convert this to grams. And just do the calculation. As you can see, the grams over here, and then you can get the volume. So moving on, we have the density, like practicals to investigate density. We have the Eureka cup and these two things. And for the Eureka cup, we have the displacement can and the measuring cylinder. And basically, you use the scales to measure the mass of the object in kg, and collect a displacement can, 2 beakers, and the measuring cylinder. And here are the steps for this Eureka cup. And for the second one, which is this, you can read the description and how to investigate the density using these cubes over here. And here's introduction to pressure. We have this equation right here. P in pressure equals F, which is force, divided by A, which is surface area. And P is in pascals, force is in Newton, and surface area is in meter square. And pressure and area are inversely proportional. So here's like a triangle, and area and pressure. So the bigger the area, the smaller the pressure, and the smaller the area, the bigger the pressure. And what pressure is created by a force of 3000 newtons acting over an area of 60 cm square? So basically you do pressure equals 3000 N divided by this, which is in meter square, to get 500,000 pascals. And what pressure is created by a force of 2 newtons? And you can have a look. Just 2 divided by 10, which is 0.2. And you can have a read of the last question. So moving on, we have pressure in fluids. So what is a fluid? A fluid, or in physics, is a substance that flows, including liquids, gases, and plasmas. And here's a simple question. If the air pressure is 100,000 pascals and the surface area of the can is 0.04 meters square, the force pushing out the can from the lesson previously, F over F divided by A, will be 100,000 pascals equals F divided by 0.04, which you get 4,000 newtons for the force. And here's a hydraulic press. A hydraulic press turns a small force into a big force through the use of fluids, and through this concept called the conservation of pressure. So you have this 10 newtons over here pushing in with 1 meter square of surface area into this thing which has 2 meters square of surface area. Using these two pistons, the conservation of pressure, you get a bigger force over here. using this equation. And here's a exam question. Use ideas about molecules to explain why the air inside the tires exert pressure. And it's a 3-mark question, but there's 5 marks to get. And you can answer any 3 from the idea of continuous random movement of particles, and they collide or they impact each other. And this happens within, with, or inside the walls of the tire. And the idea that force is produced when they hit against the walls of the tire, and the idea of pressure as a force on an area using the equation. And then we have height and pressure, and this is a starter. Over here we have this a can right here and different holes for jets. The most bottom jet will be the strongest jet because there's the most volume of water above it over here. And here's the equation. Pressure equals density times basically P equals rho GH. Pressure times density. Pressure equals density times gravitational field strength, which is 10 for IGCSE, and the depth or the height. And you can see in pascals, kg/m3, 10, and the meters. And here's a little diagram of a dam. The dam is shaped this way with a huge base over here, because the water pressure is high in the base due to this equation right here. Because as the height or the depth increases, the pressure will automatically increase. So it needs a strong base or a huge base so that the structure can support the water. And obviously the dam can shape this way where it has a huge wall right here, but due to let's say financial issues or money issue, and this way is cheaper. And here's the question. John thinks that he has come up with an amazing invention to meet a snorkel so that you can go snorkeling deeper than ever before. But when he tests it, he finds out that it doesn't work. You can breathe out through it but not in. Why? So the answer is, this is because when you're deep down in the ocean, the water pressure is high and it restricts the movement of the diaphragm, so it can't contract, and therefore lungs can't receive oxygen. And from biology, you know that diaphragm contracts and expands when during ventilation or like inhalation and exhalation. And scuba diving has an oxygen tank because the tank is pressurized and the air is forced into the lungs, which helps breathing and inhalation and exhalation. So here's energy and changes of state, which is for separate science. So what is required to change the state of matter, which is heat and energy. Heat provides the material with energy, causing the particles to vibrate, breaking the bonds that are holding them together. And if enough energy is provided, the bonds holding the particles together break completely, and the particles can move freely. So here's the name of different change of state. We have the typical melting, vaporization, or evaporation or boiling. And gas to liquid, it's condensed or liquefaction. And liquid to solid is solidification or freezing. So from solid to gas, straight away, it's called sublimation. And gas to solid is called deposition. So here's the concept of ethanol on hand. When ethanol is placed on the hand, it should feel cold, because the ethanol is transferring energy from your hand to its molecules to evaporate. And it's an endothermic reaction because ethanol goes from a liquid to gas. So the particles of ethanol takes in the heat so that they have more energy to vibrate and more kinetic energy, meaning that it will evaporate. And this means that the higher energy particles in the ethanol have high energy to escape and evaporate. And then this means that the particles left in the ethanol will have a lower average kinetic energy and therefore a lower temperature, making it feel very cold. Then we have temperature time graphs for separate signs. Endothermic means getting energy in, and exothermic means getting energy out, which is releasing energy and releasing heat. And gas particles have the most energy because they need more kinetic energy to vibrate so they can keep moving in air randomly. And here's temperature time graphs. The heat is used to break the bonds between the molecules to change from one state or phase to another. During a state or phase change, the temperature doesn't change. Over here, it's the plateau over here. Because if heat is coming into a substance during the phase change, then this energy is used to break the bonds between the molecules of the substance. The example we will use here is ice melting into water. And immediately after the molecules bond in the ice are broken, the molecules are moving or vibrating at the same average speed as before. So the average kinetic energy remains the same, and thus their Kelvin temperature remains the same. And we'll look into Kelvin temperature in a few minutes. So here's temperature time graphs again. So here's temperature, pressure, and kinetic energy. When the pressure is 0, the water temperature should be minus 273 degrees Celsius, and it's called absolute 0 or 0 Kelvin. And when the pressure is 0, it means that there's no particle movement. So here's the relationship between water temperature and water pressure. It's positive relationship because it's increasing from the water temperature and it's increasing from the water pressure. So here are 4 questions. What happens to the particles as the temperature decreases, and therefore how does it affect the pressure? So as temperature decreases, the kinetic energy in the particles decreases too. Therefore the pressure also decreases because there are fewer collisions between particles. And here's what is the relationship between temperature and pressure. As the temperature goes up, the pressure goes up too. And temperature, which is in Kelvin, is directly proportional to pressure. And if absolute 0 or 0 Kelvin is equal to the temperature in Celsius, at which pressure is 0, how do you convert from Celsius to Kelvin? So here's an equation. From 0 K, you know that it's equal to minus 273 degrees Celsius. So for the temperature for Kelvin equals temperature of Celsius plus 273. And what happens to the kinetic energy of particles as temperature increases? So as temperature increases, the kinetic energy increases too as the speed increases and more collisions between particles at the side of the container. And temperature in Kelvin is proportional to the kinetic energy. So here's specific heat capacity. Specific heat capacity is the energy required to change the temperature of an object by 1 degree Celsius per 1 kg measured in joules divided by kg times Celsius. So here's the equation. Delta Q is the change in heat energy equals mass times specific heat capacity times the temperature change, which is delta T. And delta Q is the amount of heat energy going into or out the material in joules. M is the mass of the material in kg. C is specific heat capacity, which is in this. And temperature is the material, which is in degrees Celsius or Kelvin. So here's which substance would need more energy to produce 1 degree Celsius of temperature change. So we have 1 kg of water and 1 kg of lead. But the specific heat capacity, you can see there's a huge difference. The water is 4,180 and for lead is 128. That means that from this equation, water will require 4,180 joules of heat energy and lead will require 128 joules of heat energy. So the more the specific heat capacity, the more energy it requires to change it by 1 degree Celsius. And here's a question. A kettle is used to boil 3 kg of water, and the water starts at room temperature at 24 degrees Celsius, and the kettle switches off when it reaches the boiling point, which is 100 degrees Celsius. And the specific heat capacity of water is 4,180 joules divided by kg times Celsius. And what is the temperature of the change of water, which is just 100 divided by 100 minus 24, quite straightforward. And the amount of energy supplied by the kettle is just 3 kg mass times specific heat capacity and the temperature change, which gets us this energy change. So moving on, we have investigating the specific heat capacity, and you can conduct an experiment using the specific heat capacity metal cylinder. So here are some considerations. We want as much of the heater's energy to enter the metal block as possible. This means that we must insulate and block to avoid losses to the surroundings. And we can also ensure better conduction into the metal by placing oil around the heater. And you can have a layer of insulator, like let's say plastic or any cotton wool or anything that's good for insulation of heat. And here is what must measure time in seconds to work out energy, which is power equals energy transferred divided by time taken. We also need to know the mass of the block and the temperature difference. And to rearrange the equation for C, we get C equals delta Q divided by M times delta T, which is specific heat capacity equals change in energy divided by mass times change in temperature. And here's the setup over here. And moving on, we have investigating again. Here are 2 ways to calculate the specific heat capacity. We have the standard way, which is over here, you can have a read. And the more challenging way and the more accurate way, where you can have a read for yourself, which involves plotting a graph of temperature change on the y-axis against time. And here's a question. What is the accepted value of the SHC, the specific heat capacity of the substance, and how far out is the result? And as we conduct this experiment, most of our results will be quite different from the actual value because energy losses are the biggest factor due to like not insulating enough or like stuff. And why are most people's results too high compared to the accepted value? Because the values for energy inputted that we use are too high, as more energy has been lost than we've accounted for. And moving on, we have Kelvin at absolute zero. As we know about just now, from a few slides before, 0 Kelvin equals minus 273 degrees Celsius, which is the coldest temperature, and the temperature in Kelvin equals temperature in Celsius plus 273. And Kelvin scale is a scale of temperature beginning at absolute zero. And on the Kelvin scale, the water freezes at 273.15 K and boils at 373.15 K. And at 0 Kelvin, which is minus 273 degrees Celsius, the particles stop moving and all disorder disappears. Thus, nothing can be colder than absolute zero on the Kelvin scale. And here is a little description, then have a read. And the kinetic energy of the particles in an ideal gas is proportional to the Kelvin temperature. And here's a graph. And here are 3 questions. The kinetic energy of gas particles on a hot day will increase as temperature increases, and kinetic energy will increase too. And from 10 degrees Celsius to 20 degrees Celsius, the particles will only gain a little kinetic energy as the difference is small, which is 10 degrees Celsius. But from 10 K, which is 10 Kelvin, to 20 Kelvin, the particles will gain a lot of kinetic energy as the difference is 10 K, which is 283 degrees Celsius. And name the process which liquid changes to gas, and it's boiling or evaporation. And here's described the changes in arrangement and movement of molecules when the liquid becomes a gas. In the liquid, the molecules are packed together and are linked together by bonds. They can move around freely, but when it comes to gas, the bonds got broken apart and the molecules are more further apart from each other, so they can move around more freely. And here's speed and temperature. Explain why milk droplets floating in the water jiggle about randomly over here. And it's because the water particles are constantly moving randomly and they collide with the milk droplets from all directions, so it jiggles randomly in, let's say, water. And what will happen to the motion of milk droplet if it were to raise the temperature of the water? And obviously the milk droplet will jiggle more around vigorously in all directions because temperature is directly proportional to kinetic energy. And when the water particles have more kinetic energy, they move faster. And remember, the temperature is measured in Kelvin over here. And explain why increasing temperature will increase the pressure felt on inside of a tire. Because increasing temperature will increase the kinetic energy of air particles, so they move faster in random directions. Therefore, they bump into the sides of the tire harder and faster. And because the pressure is measured by how hard the particles push against the side of an object, the pressure will therefore be high. And explain how the motion of gas particles produce pressure inside of the container. The gas particles move randomly in all directions, and it bumps into the side of the container and the movable piston, increasing the pressure and therefore producing pressure. And state what happens to the pressure if you push the piston to the container without changing temperature. It would be easy to push the piston at first, but you would not be able to push it after the gas is very compressed and the air pressure inside the container is very high. And here's 3 points. When the gas is heated, the mass of the gas particles stay the same. The gas particles move faster, and the average distance between gas particles increase. And here's pressure temperature law. And here's for starter. As the speed increases, the particles move more vigorously and collide with the side of the object more frequently and harder. Therefore, there's more force exerted, and because the force equals pressure times area, and therefore the pressure inside the area or the object increases. And temperature is directly proportional to kinetic energy and speed. So as temperature increases, the kinetic energy increases too, so the speed of the particles also increase. And here's pressure temperature law, which is the conservation of pressure and temperature. And P1 and P2 are pressure of gas, and T1 and T2 are the temperature of gas, respectively. And pressure is in PA, pascals, and temperature is in Kelvin. Wanted to know Kelvin over here. Kelvin. So here's a question. Compressed air from a can is used to clean computer keyboards. use ideas about particles to explain how the gas can cause pressure on the side of the container. And in the pressurized container, the gas particles are constantly moving in random direction, and it will collide with the side of the can, creating force. Because force equals to pressure times area, the overall air pressure in the container will then increase. And the can has a warning sign right here. How would increasing the temperature of the compressed air affect the pressure in the can? Which is the higher the temperature, the higher the pressure. And temperature is directly proportional to the kinetic energy and speed. And as the temperature in the can increases, the kinetic energy and speed will increase too. And as the speed increases, it will collide with the object more frequently and vigorously to create a more force and therefore higher pressure. And lastly, we have Boyle's law, which involves pressure and volume. And pressure is directly proportional to K over volume. So pressure times volume equals K. Or another way, pressure is inversely proportional to volume. So for Boyle's law, we note that P1 times V1 equals P2 times V2. So as volume decreases, pressure increases. And if volume increases, pressure decreases, which is an indirect proportional relationship. And here's two questions at last. A scuba diver blows up a bubble of volume of 4 cm3 at a depth of 10 meters where the pressure is 2 times 10 to the power 5 pascals. What is the volume of the bubble just before it hits the surface? And the surface is 1 times 10 to the power 5 pascals. And we know that volume is 4 cm3 and depth is 10 meters. The pressure is 200, which is this. And you can have a read for yourself to all the different things. So we know that P1 times V1 equals P2 times V2. So P1 times V1 equals P2 times V2. And the volume, the second volume is X, which is 8 cm3. And for extension, what is the difference in radius between the bubble at 10 meters and the bubble at the surface? So the area for a bubble or a sphere is 4 over 3 pi r cubed. So in this case, it's 8 cm3. You can see the radius is this. The cube root of 6 over pi, and in the surface is for this, from this part here, and in the surface is the cube root of 3 over pi, and the difference would be the cube root of 6 over pi divided by the cube root of 3 over pi, which gives us 0.256. So that's it for this IGCSE Physics series, and I hope you guys have enjoyed this solids, liquids and gases. Check the comment section down below for the pinned comment for all the timestamps, and go to the description and go check out my Instagram and drop a follow for daily content. And I hope you guys have enjoyed this, and I'll see you guys in the next video. But until then, stay safe and peace.